Good afternoon, everyone. Welcome to another of the Ground Source Heat Pump Association's webinars. We're up to about 26 in total so far, and this is, I think, the fifth one in what we've called the open loop sessions. This is going to be the last for the time being, so we'll be scratching our heads looking for new ideas, and/or possibly run some repeats of the more popular ones that we've done so far. Okay, the talk this week is going to be given by Chris Davidson of Genius Energy. Some of you may have seen him in previous presentations, if not in his prior existence in any case. Chris has a wealth of experience in ground source, both in closed loop, larger closed loop, non-domestic systems, but is going to focus today on talking about the above ground elements. So what goes on in your plant room when you're dealing with open loop systems. So there are some significant differences in what goes on with your heat pumps associated with open loop systems. Just some admin stuff. We don't expect any fire drills today. So if the alarms go off, do a runner. If you could activate your mute buttons to keep the background noise down, it would be helpful. And if you've got any questions, please submit them using the chat button, and I'll attempt to lob them at Chris when we get to the end of this. So many thanks for joining us all. Without any further ado, over to Chris.
Thanks very much indeed, Robin, and thanks for a great introduction. And welcome, as Robin says, to the final session for this year for the Ground Source Heat Pump Association webinars. And this one will be the last one of a series of 5 on open ground source systems. And as Robin says, this is all about what happens above and beyond the ground. But first, I'm going to summarize very briefly what's going on in the previous 4 sessions to set the scene. So in session 1, it was myself. And the idea of that session was to allow you to understand the decision-making process to get to the point where we're considering open loop as our primary option for that project. And so the key messages there were: how much water do we actually need to deliver the heating and cooling loads that we are looking at? How much water is available in the ground, or how much water do we think is available in the ground? And just gave you some ideas about what these systems actually look like. The second session was very entertaining, I found, and hosted by Hugh Williams. He talked about groundwater modelling. And the key point he was trying to get across, I think, is that whilst models can be accurate, they can never be perfect. And the way that Hugh put it, I think, which was very insightful, was to say, how wrong your model is really the question, or how far wrong your model is more the question rather than how accurate it is. So that was a very useful session. The third session, again, very entertaining, by Dave Banks, and that was talking about the use of mine water in these types of systems. So the majority of the rest of what we've talked about is applicable to surface water and boreholes, but that session was specifically about the mines in the UK as a resource for heating and cooling. And I think the key message that Dave got across there was: go into this with your eyes open. If you are getting involved in mine workings, because they are there, it doesn't necessarily mean that it's the best solution for you. So go into it with your eyes open as to what the challenges are in terms of accessing that mine water, and also issues like water quality, for example. Not to say it's a bad idea, it's a very good idea, but you need to go into it with your eyes open. The 4th session last week was hosted by John Finlay, and he talked about how we go about constructing boreholes for water source heat pumps. He also talked about the legislative requirements as well. Really entertaining session, so it's worthwhile, if you haven't seen that, going back, not just for that, but all the 4 previous sessions. So finally, listen on. We're going to go into above and beyond the ground for open loop ground source heat pump systems. At this point, I'd normally ask for audience participation and all those kinds of things, but I'm just going to have to keep talking as we have done in previous. So first of all, a word on water quality. This rather poor picture, I'm afraid, here is a cone that is used to work out how much particulates are in water. And I'll deal with particulates first. So there's three types of water quality concerns that we generally have with open loop systems. So particulates, if you've got a water well that's generating sands, for example, or any other particulates, then it's really a well development issue. And John talked about well development last week in a bit of detail. So that's how, once the drilling operation's finished, is that well then put to use. And one of the key elements there is that really that well isn't developed properly and fully or properly constructed until you've got no particulates in solution. They will be the absolute bane of your life for the lifetime of that system if you do have them. And filtration is absolutely the last resort. You should really use filtration, I mean above ground filtration, as the last resort. All the particulates and all those elements should be filtered out in the well construction itself. So that's just a word on particulates. Secondly, minerals. You can do upfront assessment to work out what the mineral content of that water is going to be, but ultimately, until you get a sample and analyze it, there is an element of uncertainty. The analysis of the water is really important as part of the construction process, because then that informs the specification of the components in the plant room, how regularly those components are going to have to be maintained, and put frankly, high minerality in an open loop system can be as bad as shutting the system down. So it really needs to be risk assessed as part of the other elements of the system design and construction. And then finally, bacteria. Bacteria can live in water wells. Unfortunately, there is a bacteria which eats iron, and it can live in water wells and turn a water well to sludge. There are treatments available for wells that are suffering from bacterial contamination, and you would need to put in, if this did happen, you would need to put in a treatment schedule that would deal with that adequately. So I mention those really because all of those elements have a bearing on what happens above ground and how we build the architecture of our open loop system. So let's start with the simplest of the configurations of open loop system. What we've got here is, I've just drawn a couple of water wells here. One with a pump down it, which is taking water from the ground. It's then going straight through the heat exchanger and the heat pump and then being put back into the ground. Now, what the implications of this is this untreated water here is hitting the heat exchanger and the heat pump. And if that heat exchanger isn't designed to deal with that water, with the minerality and so on that's in it, then it's going to fail very, very quickly. And replacing a heat exchanger inside a heat pump because you're having to cut into the gas refrigeration cycle can be quite a costly exercise. So whilst there are heat pumps that are designed to take groundwater directly, they are less common, and they would need to be specified specifically for the water that's encountered in the borehole system you've got. The benefit, of course, of doing it is that you are taking that water in directly, so it's got a minor efficiency benefit, but also it's a cost benefit. You've only got one box in the plant room. You don't have other heat exchangers and so on. So that would be the simplest of all the architectures, but it does have its limitations, particularly anything of scale. And that's why you generally tend to find a heat exchanger between the two circuits, sorry. So in this case, again, we're taking water from the ground with a submersible pump. That groundwater is now going through a heat exchanger and back into the ground. And we now have what is effectively an internal closed loop that's feeding the heat pump. And the benefit of that is that we are now keeping the water, the groundwater, away from the heat exchanger inside the heat pump, and we can specify this heat exchanger to be maintainable far more cheaply than it would be if you had to replace the heat exchanger inside the heat pump. So most open loop systems tend to be of this type of configuration. You've then got decisions to make as to how you deploy your heat pumps themselves. So for example, this is a central plant solution. You can see the water wells here feeding the heat exchanger. Then the heat exchanger keeping an internal closed loop which feeds the heat pumps. And in this instance, we've now got a high temperature distribution system up through the building to heat interface units, for example, in an apartment like this. The benefit of this system is that all the plant is centrally located, and you've got a more conventional district heat type approach. But you do have some other disadvantages as well. The cost of these heat interface units is not insignificant, for example. Also, this pipework has to be very well insulated to deliver that heat up the building. There's also quite commonly reported problems with the risers and the communal areas in which the risers tend to be located actually overheating in the summer, because this district network needs to be running all year round to deliver domestic hot water. The other disadvantage of this type of system is that the heat pumps need to be delivering water at the highest temperature required for the whole building. And that generally is the domestic hot water production temperature. So it can have an adverse effect on efficiency. The alternative approach is to actually take this internal closed loop and now extend it through the building. This is often called an ambient temperature network or a fifth generation district network. And in this instance, rather than putting heat interface units in the dwellings as they are here, or it could be in spaces around a commercial building, what we're actually doing is putting a heat pump in situ. And the big benefit of that, it eliminates the overheating problems in communal areas, as I mentioned earlier. But the big benefit really from an efficiency point of view is that these heat pumps will only be doing what they need to do in terms of temperature. So there may be some spaces that are more difficult to treat than others, which need a higher temperature of the heat pump. And also when the heat pump goes on to domestic hot water, it only runs at that higher temperatures when it's actually doing that. So rather than running at that high temperature all year round. So there's two different architectures, and these architectures are applicable to both closed loop and open loop. But I just wanted to show you them in the context of open loop, so you can see what's going on. If you'd like to see some case studies on these types of approaches, one of our members, Kenza, has got some great materials on their website if you'd like to see some of the deployments. We're just completing a job in Sunderland at the moment for 7 apartment buildings up there with them. So just if you want some more background information, please do have a look at their website. So let's now talk about heating and cooling systems. So these are systems where we've got either simultaneous or diurnal heating and cooling requirements. So typical commercial building in the UK. There's generally 2 architectures that are used for this. Same as before, we've got our external closed open loop, We've then got our heat exchanger, keeping the 2 circuits separately and transferring energy between the 2. And then we've got our internal closed loop. In this instance, what I've shown here is a couple of heat pumps dedicated to heating and a couple of heat pumps dedicated to cooling, and they will cycle on and off to meet those loads in the building. What's actually happening here is that the cooling heat pumps are putting heat into this loop and the heating heat pumps are taking heat out. So you can see that if we've got some kind of balance of load in that building between heating and cooling, then we're actually not involving the ground. Now that balance might not be perfect, in which case we'll need to run the ground pumps to an extent, but we perhaps wouldn't be running them as quickly as we otherwise would be. And that brings me on to the control of these systems. I've seen an awful lot of people get themselves in a terrible pickle as to how you control a system like this. And the old adage, keep it simple, is the best message I can give you. In practical terms, what we actually do is we look at the temperature of this closed loop here, and we turn the well pump on to moderate that temperature. So all of the requirements that John talked about last week in terms of the licensing, in terms of temperatures, in terms of instantaneous flow rates, annual flow rates, and so on, are all design parameters now rather than controlled. So rather than trying to control what this water temperature is, we know what this system is going to be delivering. And so we actually design in those limits that are required by the Environment Agency. But it keeps it tremendously more simple by just monitoring this temperature for a high limit and a low limit, and then running the pump down the well to maintain that within a bound that we are happy with in the system. So most of the open loop systems I've been involved in are like this. You can also get clever by using reversible heat pumps, for example. A reversible heat pump, effectively you switch the pipes over on the compressor, so the evaporator becomes the condenser becomes the evaporator, and it can switch from heating to cooling, so you're getting double benefit from the plant that you're deploying. There is an alternative approach that does have some advantages. Looks a little bit more complex, but actually it's pretty straightforward. What we've got here in the middle is a heat pump that isn't reversible, and its job in life is to take heat from these cooling circuits and put them into the heating circuit. So it's taking heat directly from any cooling that's going on in a server room, for example, and it's delivering it into the building. And what we actually do is we connect the open loop circuit to either the hot side or the cold side, depending on whether we've got an excess or a deficit of energy. And it simply adds or takes away the energy that isn't needed. Now, this can have efficiency benefits. The heat pump can be optimized to deliver this. You need a variable speed drive heat pump for it to work reliably, but it is a very effective way of delivering both heating and cooling into buildings, particularly commercial buildings. So just in summary, this is a water well system that is, this is a water coming from the ground. And so what are we going to do with it? Well, the first thing you really need to do to consider is you really need to engage a specialist team. I hope that the main message that's come out of the last 5 webinars, including this one, is that these things are non-trivial. They are not simple. They are not very simple. I'm going to turn the sound off because it's distracting me. It's not a simple thing to do. You do need a professional team. You need experts in their fields, from licensing, modeling, designing these systems, right the way through to installing them reliably. The second thing that I would get across is establish your viability very early on in the project cycle. So get that geological analysis done and work out, is it even feasible to get 20 litres a second in that part of the UK? Because if you don't have a viable scheme, you know, it's not worth proceeding with. Secondly, get that licensing process going with a specialist as soon as you possibly can. The Environment Agency pre-application process is actually really good. It does save an awful lot of time, and they will tell you at very early stages, and free of charge as far as the Environment Agency is concerned, if they see problems with granting that license as the project proceeds. Remember that modelling can be done. In its simplest form, no modelling would be required, or a very simple set of modelling, as I outlined in the first of these 5 sessions. Or it could be very complex, like Hugh kindly demonstrated a few weeks ago. And just bear in mind that, as with building modelling, there is limitations to it. I often say to building services engineers, you know, they give me an IES hour-by-hour model of a building, and I say, here, if you expect to go to that plant room on the 10th of July at 11 AM and see it doing exactly what it says in that box, then you're misunderstanding what that modeling is about. So modeling can be simple, it can be complex, and it's never 100% accurate. Water quality is a key consideration. It's very important to design your system from day one to deal with the water quality that you're expecting from that location. And also it's important to revise the specification of things like the well pumps, the heat exchangers and so on, once you've got a concrete analysis of that water quality. And water quality, as I say, can shut a system down. It needs to be considered is a very important part of the system design. Keep it simple, as I say, particularly with controls. Don't overdo the control of these systems. The simpler you can keep it, the more complexity you can get out of it, the more likely you are to have a successful installation. Remember also that the Environment Agency process post-installation can take up to 9 months. So that's once you've got your wells installed, before you can start fully using those wells, it can take up to 9 months. So make sure you build that into the program. And of course, with the end of the renewable heat incentive coming up very soon now, it may actually be difficult to get a system installed and licensed before the end of the renewable heat incentive, even as we sit here today. And then finally, just to re-emphasize, get professionals involved in this. It's not something to be taken lightly. If you're a main contractor, if you're a building services engineer, by all means, get involved in the project, but my best advice is to get people who know what they're doing to work with you. So if I could ask Robin to ask any questions. Oh, you're on mute, Robin.
Press the unmute button. Hello. Thanks, Chris. It's a great summary and walkthrough of what's involved with these systems. I haven't got anything flashing up on my screen, but if I could pop a couple of comments and just add to Chris. I think what you'll have found is that in essence, open loop systems are thermodynamically very attractive. They are very good news if you can get hold of that water and get rid of that water. And typically from what you've seen in the 5 sessions is that on the whole, they are very useful for the larger systems. So larger systems in urban areas where you've got constrained areas of ground or very limited ground, if you've got the water resource there below you, then it's going to be a great thermo resource for you to use. But the big message is, as Chris emphasized towards the end there, is that somebody has got to prove the resource first before you can go ahead. And somebody has to spend real money proving that resource. So you need to warn your client that they're going to be in for some money up front before you can get an answer either from your specialist or from the Environment Agency as to whether you're going to go ahead, which is kind of why these systems tend to fall into a place for larger systems where that kind of funding is available. I would just repeat my bête noire that some of you know I'm known for, is that while they're very good thermodynamically, because you've basically got quite good high temperature water for heating or cool water for cooling, you need to bear in mind the pumping energy for these systems. So don't get too carried away with very deep wells where you've got to go a long way down to the groundwater and you're going to have to pump it a long way. So bear in mind and think about what the pumping energy is going to be for your system. And the big plate heat exchanger that Chris showed up there, you've got to take account of the pressure drops in that heat exchanger. Otherwise, you're going to be sacrificing some of your efficiency. I think the last thing I would just throw in there is to make people aware, people who may be coming to this or potential clients who might be interested. There is a best practice guide available from CIBSE, developed by CIBSE and the Ground Source Heat Pump Association on these systems. It's Best Practice Guide 3. People may find that quite useful as a checklist of what you need to go through to successfully develop these systems. And I'll shut up now. I haven't got any other questions popping up in the chat box. I would like to thank Chris and the other 4 presenters on Open Loop. It's been a really good group of presentations on this particular topic. This will, as Chris said, this will be the last of our webinars for this year while we go away, scratch our heads and think anything up for next year. If you've got any ideas on topics that you would like to see, please get in touch with the association or bug any of us, and we'll see what we can do for next year. So on that note, I'd like to thank you all for logging in and viewing this session, and wish you all the best for the season, and hopefully we'll see you all again in the new year sometime. Thanks very much.
Thank you, Robin.